In today's video, we're going to start discussing the concept of identical particles. This is chapter 13 in the book, and it's a really important concept in modern physics and quantum mechanics. The fact that quantum mechanical particles are indistinguishable. There is no measurement that you can make. If you have a system of two electrons, say, there is no measurement you can make that can tell which electron is which, right? And just that idea alone has some pretty huge repercussions in the way systems behave. For example, if you look at different materials like metals and semiconductors and how you would treat those just using statistical mechanics, um, the fact that they're indistinguishable leads to a lot of the different properties we see they have. It also relates to how we treat them quantum mechanically, obviously. For example, if you consider two electrons, so identical particles, both spin one half particles. So let's say we have two spin one half particles. We've discussed this system a few times before. And one of the ways we've looked at it is we've considered the uncoupled bases, where we can have, both electrons are spin up, one electron spin up, one spin down, and one spin up, and both are spin down. So this was our uncoupled bases, right? And if you're like me, you probably intuitively tried to think of this as, all right, well, the first quantum number that m sub s1 is the spin on the first electron, and this one refers to the spin on the second electron. So in this case, we have electron 1 is spin up, electron 2 is spin down, and in this state, we have electron 1 is spin down, and electron 2 is spin up. But if these particles are truly identical, which they are, and indistinguishable, we can't really think about it that way, right? I can't say particle 1 is spin up and particle 2 is spin down, because there's no possible way I can know which particle is which. I can't number them as particle 1 or particle 2. The only way I'm really able to think about this is I have two particles, one of them is spin up and one of them is spin down, and there's no way to tell the difference between which one is which. I sort of have to think of just the number of them that have the spin up and the number of them that have the spin down, not necessarily which ones are which, right? So you can sort of think, all right, it might be more appropriate to describe, if you're sort of thinking about these in that naive particle one's up, particles two's down, it might be more appropriate to sort of think about these states in terms of our coupled bases, where we have the spin up and the spin down plus the spin down and the spin up states, or the other coupled basis state that has those two, where it's minus those two states, right? These are in the J total spin and coupled bases. These are the 1, 0 and the 0, 0 states. And if you think about it, now we're not saying one particle has one property, the other has the other. And we're just thinking about it this way. Now we've just been sort of talking colloquially about how we think about these things. We can the only difference between these states is this plus or minus sign. And we're going to follow the way the book sort of introduces this concept of identical particles by using this as an example to discuss what's called exchange, and what we're going to call the exchange operator. So we can think about an operator called the exchange operator that we're going to call, in general, we could just be Pij, where what this operator does is it takes your system of particles and it switches the ith and the jth particle. So in this two-particle system, what this is going to be is P1, 2, and if this operates on our two-spin system where we have S1, S2, M1, M2, what this operator does on that system is it exchanges, hence the name, those two particles and produces the ket where those two particles have been switched. So it switches those. So if we can now think about applying this exchange operator on these two states here. So if we take P12 and operate it on either of these states, the let's start with the 10 state. This ends up being, well, 1 over root 2 comes out in front, and I have P12 plus minus plus P12 minus plus. And this ends up just being, well, it's the exact same state. This ends up being 1 over root 2 minus plus. It's exchanged those two quantum numbers for those two particles, and plus minus. It's exchanged those two, which is the exact same state we had. And we can see if we do the same thing to the 0 state, we get the exact same thing, except for this is now a minus sign, so it ends up being negative 0, 0. So both of these states are eigenstates of this exchange operator, and they have eigenvalues of plus or minus 1. Right, so the 0, 0 state is an eigenstate with eigenvalue minus 1, and the 1, 0 state has the eigenvalue 0. If you think about this, this is consistent with the concept that there is no measurement we could make that could possibly distinguish between those two states, right? If we think of the probability, let's say there's some outcome that projects that of a measurement that projects the system into some psi n state, the probability of measuring, one of these two states, we'll call, the 1, 0 state, we'll call that one psi plus, because it's got the plus sign here, and the 0, 0 state, psi minus. Well, if we were to take the probability of measuring one of those states, and it producing the result that is given by this psi n, whatever that result is, squared, we get that. If we take the exact same system and exchange those two particles, right, the probability of that result having the exact same outcome is just going to be, well, throw in that exchange operator, squared, and since these are eigenstates of that operator, this is just going to be psi of n plus or minus 1, that state, squared. This plus or minus 1 gets squared away, and we end up having the exact same probability that we had if we hadn't exchanged those two particles. So and this is for just a general measurement of, that produced some result. There's no way that exchanging the particles changes the probability of anything we're measuring. So it's kind of consistent with the idea that I can't make a measurement that's going to tell which particle's which. But, we've also discussed how these two states, they have different total angular momentum, right? One has the total angular momentum of 1, one has 0. We can measure those differences. So although we can't make a measurement that's going to determine which particle is which, they don't represent the same state, right? So the question sort of becomes, well, which sort of states are going to describe which types of systems? And that's going to relate to this exchange operator. The way it relates to the exchange operator is essentially from the what we call the symmetrization principle, or postulate for us, which essentially says that the state vector of a system of particles must be either symmetric or anti-symmetric under exchange. So essentially what it's saying is, if I apply the exchange operator to some state vector of some system of particles, I am either going to get that system must be an eigenvalue of that operator, and it's going to either be symmetric and have an eigenvalue of +1, or anti-symmetric and have an eigenvalue of -1, right? And essentially what that means, this property of symmetric or anti-symmetric under exchange relates to this spin property, and that symmetric systems that are symmetric under exchange have what are called they have integer spin values. So integer spin systems are symmetric under exchange, and they form systems of what we call bosons. And if they're anti-symmetric, they have half integer spin, and as you probably are familiar with, those are fermions. So if we have a system of particles that are half integer spin particles, they are going to be anti-symmetric. That state function that describes that system is going to be anti-symmetric under exchange of any two of those fermions, and that leads to a lot of properties. It's related to the Pauli exclusion principle, as we'll see later on. So this all comes from the symmetrization principle, and relates to what we've been saying. If you've been following really closely and critical, this might start to seem like there's a mistake here, right? We just started this whole discussion saying, well, we're talking about, two electrons, two spin one half systems, and we have these two states. One of these states, these spin states, is symmetric under exchange. We showed that the exchange operator on that system acting on the 1,0 state is symmetric under exchange. But we just said that systems of half integer spins like this one must be anti-symmetric under exchange. So this seems like a conflict, but we have to be careful. This symmetrization postulate here, this is the exchange operator acting on the entire state vector. And we've only been looking at the spin state vector. So this system of electrons is going to have, its state vector is going to have multiple parts to it, right? It's going to have a spin part, the part that we've looked at, the state vector that describes the spin subspace we're looking at, and it's also going to have sort of a spatial part to it as well. The part of the state vector that relates that sort of wave function or position representation that we've been talking about. And when we apply this symmetrization postulate to that and perform the exchange operation on that state vector, we're doing it to the entire state vector. So what that says is, although the spin part of this wave function, of this state function, is symmetric, that just means that the full state function, when I include the spatial part, that spatial part must be anti-symmetric because the entire state function is anti-symmetric. So if I take that, basically if I take that exchange operator and operate on the state function, I'm taking it and operating it on the spin and spatial parts of that wave function. And for fermions, they have to have opposite, they can't have the same symmetries under exchange, right? If the spin is symmetric, the spatial part must be anti-symmetric. So you get that 1 and -1, so the whole eigenvalue would be -1. If they were both anti-symmetric, they'd cancel, and the state function would be symmetric. But anyway, the point being that we have two types of identical particles, and it's determined by, if you have a system of those particles, is that system going to be symmetric or anti-symmetric under exchange, where we're looking at the entire state function of the system. Now this has, surprisingly, maybe, this has quite a few repercussions, as I've been saying. So to see how this physically actually matters and changes a lot of things, consider two particles in a 1D potential where each individual particle, we'll say they're non-interacting, so each individual particle has a Hamiltonian that's described just by its kinetic energy, and they're existing in some one-dimensional potential, right? So this has time-independent Schrodinger equation or energy eigenvalue equation of the single particle Hamiltonian acting on some energy eigen function, It gives us the single particle energy value and its energy eigenfunction. It gives us that. Now, if we have two particles that are non-interacting, so there's no new potential by putting them both in the system, we'll just make that simplification. Now, we have that system Hamiltonian is going to be equal to just those two individual particle Hamiltonians, where we're going to have P1 squared over 2m plus Vx1 plus P2 squared over 2m plus that potential at x2. So remember, we're looking at one particle is a particle is at x1 and the other particle is at x2. So these subscripts, we kind of want to think about as we're identifying different locations in space. We're not identifying particles. And one of the particles has a given momentum, and the other particle has a given momentum. Again, we're not saying which. And this Hamiltonian, this system, is going to have an energy eigenvalue equation of that Hamiltonian, and it's going to have this system wave function that depends on as a function of two positions that gives us the energy of our system times that wave function at those two positions, right? So this is a bit, this wave function here, this system, the wave function for the system is a little confusing, right? In our single particle stuff we've done so far, like these energy eigenfunctions here, we're looking at essentially we have some probability amplitude that we can think of as, well, this is the probability amplitude, and if we can think about the probability density of psi of x squared as being sort of the probability per unit volume, or the probability that if we were to make a measurement of the position of that particle, it would be found at x. Well, we have multiple particles and that, so this has a little more complicated or abstract sort of idea. It's again, this is going to give us a probability amplitude, but this is the probability amplitude of if we were to measure the locations of all the particles, we would find one of them at x1 and one of them at x2. So it relates to a probability density that is sort of in two dimensions squared, where this is giving us the probability that one particle is found at x1 within some region of space dx1, and the other particle is found at x2 in some region of space dx2, right? And this means that our normalization for that system wave function would be integrating from over all space over both of those sort of, it's a one-dimensional system, so they're lengths, but essentially volumes of that system. So we would have x1, x2, that probability density squared, dx1, dx2. That has to equal 1. If we were to measure the positions of these particles, if we were to measure the positions of these particles over all space, we're going to find both of them, is essentially what this normalization constant says. Anyway, that aside, over. Back to our thing. So if we have these two non-interacting particles, and we look at the energy eigenvalue equation, we essentially, since they're non-interacting and that Hamiltonian is just going to be h1 plus h2, this allows us to write the x1, x2 as just the product of x1 and we'll call this NA and NB so we know the different ones, and x2, right? Just the product of those two, if we're thinking about this two-particle system. So this energy eigenvalue equation, sorry, I'm kind of getting sloppy here. Let's separate these two. This energy eigenvalue equation becomes H acting on that wave function, two-particle wave function, is going to be equal to E, whatever the energy of this one, NA, plus E and B times that wave function again. So x1, x2. Now, this is what we would expect if these particles were distinguishable. But again, since we're talking about quantum mechanical particles and that, we need to consider whether this spatial part of our state function is symmetric or anti-symmetric under exchange, right? And essentially, we can make that using these wave functions the same way we kind of did with the spin states that we previously discussed, right? If I want to look at the sort of spatial part of the state function, if it's anti-symmetric, there's going to be some normalization constant out front. We'll call that just NA, but it's going to be the anti-symmetric combination of these two sort of single particle states that make it up, right? This is going to be the NA x1 and B at x2, and then we're looking at the anti-symmetric one, so this is going to be minus NA at x2 and NB at x1, right? And likewise, if I were to do the symmetric part of this wave function, it's going to be the same thing, but a plus sign. It's the symmetric combination of those two. Right, and we can just, this is the position representation of that. We could just write this as psi NA NB. This would be anti-symmetric at x1 and x2, and then this one will be NA and B symmetric x1 and x2. And both of these states, if we were to plug it in and look at the energy of these, would have the energy of NA and NB would be just the sum of those two, the energies of those two individual states that they're in. So this is all well and good. What does this actually mean with respect to things? So let's consider what's the ground state of this system, right? So let's say the ground state of those individual particles is the n equals 1 state, right? The lowest energy we can have is if both particles are in that lowest ground state system where they're in n equals 1, in which case our symmetric state would be, psi 1, 1, x1, x2. The symmetric state like that is just going to be, well, the normalization would be 1 over root 2, but we're going to have that bracketed term is going to be psi 1 x1 psi 1 x2 or plus 1 x2 1 x1, right, times that normalization, that symmetric normalization constant. What this is going to boil down to is that normalization constant is going to end up being 1 because these are already, the individual ones are normalized. But the gist is this is just 1 x1 and 1 x2, right? That's the ground state wave function, the spatial part of the wave function. If we look at the anti-symmetric spatial part, this becomes a minus sign, and we end up with 0. So psi 1, 1 anti-symmetric x1, x2 ends up being equal to 0. So there is no way we can have a anti-symmetric spatial part of our wave function when both those states are in the ground thing. So this has physical repercussions. Just that symmetrization postulate has some significant repercussions. Significant repercussions if we're considering a boson or a fermion system. So if we were to take just a simple boson system, and let's take a very simple one and just say we have two spin 0 particles, right? So we have total spin of S1 equals 0, S2 equals 0, total spin of 0, so the Z component is also 0. So that's our ground spin state. That's the for bosons, that's our spin part of our state function, and it is a symmetric spin state. So if we look at the ground state of this wave function, the total state function is going to have this symmetric part of the spin state, and it's going to have this symmetric part of the position in the position representation. So we've one, the symmetric wave function x1, x2 there, and this is a goofy notation where I'm in bracket notation for the spin space and the position representation for the spatial part. But this is what our ground state would look like for bosons, right? We have both of these states are symmetric, so the total state, both of these parts of our state are symmetric, so the total state is symmetric, and we have that bosonic ground state. If we look at, say, fermions, and let's say we're just looking at two electrons, say, or two spin 1/2 particles, our spin part of our wave function is S1 is 1/2 particle, S2 is a 1/2 particle. The M1 is going to be equal to, excuse me. There's four possible states to do this, right? We can have if we look in that coupled bases, these could be the 1,1, the 1,0, the 1-1, or the 0,0 state. But since the only possible spatial part is the symmetric part, since we're looking at the ground state, we know the spatial part of our state function is going to be symmetric. We have to look at the anti-symmetric possibilities from here, and the only anti-symmetric one is that 0,0 state. So that's going to be, the total spin S is equal to 0, and the total Z component is equal to 0. So that 0,0 state is the fermion one, and this is anti-symmetric. And you kind of see how our notation is going to be giving us a problem, because what the book and I will colloquially, sort of shorthand be using as just these 0,0 states. They actually refer to different states, right? This is total spin 0 states. This is two spin 1/2 particles. So there's a difference there. But I digress. Essentially, what happens is if we're in that ground state, and we're thinking about the fermions, we have to have an anti-symmetric spin part, a symmetric spatial part. This is going to be, the only possible position wave function for that ground state, and our symmetric 0,0 state. And this requirements in the ground, what this is essentially saying here is that the ground state of a system of fermions is going to have an anti-symmetric, the ground state of one of these systems has a symmetric position spatial part of the wave function. So the spin part has to be anti-symmetric. So, sorry, repeating that, for a two-particle system, what we've sort of shown here is that the spatial part of that state function has to be symmetric under exchange. And that means for fermions, for say a two-particle fermion system, the spin part is going to have to be anti-symmetric, right? So that's the ground state, which is all well and good. But now let's look at the excited state. So if we look at the first excited state, right, we have the same sort of thing. If we're looking at bosons, we need our state function to be made of symmetric parts or both antisymmetric parts. Um, so if we're looking at that, two spin zero states, though, there's only really that 0, 0 spin state, which is symmetric. So that means our spatial part uh, of our state function has to also be symmetric, which essentially tells us, we're looking, the first excited state is going to be one of the particles in the ground state and the other particle in the first excited state. So we have N1 and N2. So this is going to be our 1 and 2 symmetric x1, x2 wave function, which is going to be 1 over root 2, 1 at x1, 2 at x2, plus 1 at x2 and 2 at x1, right? So we have essentially for our two bosons that are spin 0, so two spin 0 bosons, we have one possible state. We have only the symmetric possibility for the spins, so we can only look at the symmetric combination of the 1 and 2 individual particle eigenfunctions, um, and we get one state. If we look at that similar fermion, two spin 1/2 states, we have a totally different case, right? We again, the spin part, there's both so our spin part of our state function can be that 1, 1, 1, 0, 1, -1, and 0, 0 in the coupled bases. Those are four possible spin states. And so we have our triplet states that are symmetric and our anti-symmetric singlet states. So we have state functions that can be composed of, we have a 1, 2 symmetric and anti-symmetric um, spin and where the state, the position function is symmetric, x1 and x2, and the spin part is anti-symmetric. So that's, this function here with our anti-symmetric spin part. And then we have three possible ones where the spatial part is anti-symmetric and the spin part is symmetric, and that is our anti-symmetric spatial part. And this can be any of those possible m values, anti-symmetric or symmetric spin part, anti-symmetric state part, where that again, that anti-symmetric wave function is just that 1 over root 2, the individual particle eigenfunctions minus that. And there's one state here and three possible states here. So the first excited state for this 2 spin 1/2 fermion system is fourfold degenerate, while for a 2 spin 0 boson system, there's just the one possible state there where we have the symmetric spin and anti-symmetric spin part. So, and this actually, you know, so obviously we have different numbers of states, but this also has meaning when it comes to what these states actually look like in space, right? So let's look at, we've been talking about general one-dimensional systems right now. Let's look at one that we're very familiar with, particles in an infinite well, right? So we have those, the individual particle states look something like this, that in n equals 1 state, and then we have that n equals 2 state, right? So if we have two particles in that state, right, we know that n equals 1 state, or just in general, those states are square root 2 over L sine n pi over L x, right? So if we look at, our ground state 1, 1, x1, x2 probability density, and that if we were to calculate that, that's going to be 4 over L sine pi over L x1 sine pi over L x2, right? And if we, wanted to say plot that density, probability density, it's going to look something, what the heck? It's going to look like this. Right, where we essentially are taking the probability density for, if we look along x1, this is a two-dimensional probability density, even though we're looking at a one-dimensional problem here, because recall, this is the probability along this axis of one of the particles being found in the volume dx along in, a given region of space dx1, and the other particle being found along the, in the same dimension, but, the other particle found in, say, that region dx2. That would give us, where x1 and x2 are. That would give us some point on this as our probability amplitude. And we see, like we found, that is symmetric. That ground state wave function is going to be symmetric. If you look at this line where both particles are found in the same position, where x1 equals x2, we're symmetric about that. If we go to our, if we then look at the first excited state, right, we have some, it's going to depend on if they're symmetric or not, right? If we look at the different possibilities, depending on whether we're looking at bosons or distinguishable particles, right? So if we walk through this figure, this is figure unnumbered here. Which one is it in the book? This is figure 13.3 from the textbook. We have a few cases, right? If we look here, this is our classical situation. We have distinguishable particles. Distinguishable particles. So we know, we can tell which particle is which. And essentially, we're going to say particle 1, we'll say x1 is in the ground state, and particle 2 is in that first excited state. And if we look, I'll redraw it here, at what our wave functions for the individual, well, that was horrible, or the wave functions for our individual particles look like. The ground state looks like that. The second one looks like that. So the probability densities are going to, you just square it. So it's going to look something like this. And this one's going to have two humps sort of thing. Those are the probability densities. We're looking at those two totally separate and independent probability densities, where any line cut for x1, we get that probability density. And if we take any line cut through x2, we get the probability density that that particle is in the n equals 2 state, and the first one's in the n equals 1. However, if we, and the other degenerate state is the same thing, but just switch those particles. So now x2 would be in that ground state, and x1 would be in that first excited state. And that's sort of the probability density we're looking at. However, if we go to the quantum particles, we get very different things because of this symmetrization sort of property, right? So if we look at this, this is if the wave function is symmetric under exchange. So we're looking at the one produced by this symmetric x1, x2 state, right? So it's going to be this combination, again, where the one state looks like this, the two looks like that. Excuse me. But if we look at the details of what that function is, remember it was that 1 over root 2 psi 1 x1 psi 2 x2 plus psi1 x1 psi2 x2. If you notice, if we evaluate that at x1 equals x2, we're essentially just going to, this is going to give us a probability density that is just those two squared. And we see that if we cut along that line here, we have some finite values where this is non-zero. Essentially, what it's kind of more telling is if we look at the anti-symmetric combination of those two, we're going to have this minus sign here. So we have psi1 x1 to x2 minus 1 x1 2 rather 2 x1 times that 1 over root 2. If we look at, evaluate that at x1 equal to x2, that equals 0, right? These two terms are going to be the same. And that's why, if you look at this, there is no possibility of measuring the system where the locations of those particles are the same. This is 0 by, necessity. The anti-symmetric under exchange wave function doesn't have the possibility that these two particles are measured at the same location. This is essentially Pauli exclusion. If you have a fermion system, you can't have a symmetric spin state. So anytime you have the two particles where they're in the same, both are spin up or both are spin down, if you have those, or even the symmetric combination of the two, if you have a symmetric spin state like that, the position space, the spatial part of your state function has to be anti-symmetric, which means that they cannot be at the same location. So if you have two particles existing in the same spin states, they can't exist in the same spatial location. And that essentially gives us Pauli exclusion, and it all comes from the symmetry under this exchange operator. So that's sort of a big takeaway. Essentially, recap, we've discussed a lot. The major, I guess, takeaway from this at this point is quantum particles can be identical. If you have two electrons, there's no way to distinguish which is which. And the way we sort of treat these systems is we're going to have, anytime you have a system of quantum particles, you have to consider whether they're bosons or fermions, which is set by how they behave under this exchange or under exchange operator. If you exchange any two particles, if you exchange any two fermions, the state function of that system must be anti-symmetric under that exchange. So whereas for bosons, it must be symmetric under that exchange. And we end up just from that seeing a lot of different properties arise. The big one you're probably familiar with is the idea of Pauli exclusion, and the fact that, let's say we have two particles that are fermions, because the state function must be anti-symmetric under exchange, if you have symmetric spin states, which includes any time those two particles have the same spin state, they cannot exist at the same location. They sort of repel each other with this Pauli exclusion thing. In upcoming videos, we're going to extend this. We're going to discuss about that, what we would call the exchange interaction here, and then start thinking about interacting particles. Right now, we've just been discussing, two particles that don't have any, Coulomb interaction or any interaction between them. We're going to discuss what happens if you allow for interactions in that and build on this. If you have any questions, feel free to email me or bring them up in the synchronous sessions. I will talk to you then.